these guys joined the team, and we've had some pretty amazing phone calls about companies wanting to work with us to offer their power solutions to the market. So we think we have a very compelling opportunity here because we're not the manufacturer, which is, I think, a very good thing, because we can pull from different suppliers depending on what we're looking to achieve. So, I mean, you know, our business, it's all about the right tool for the job. That's what we're here to help you guys with. Obviously, Jimmy and Vince are aces in this and working with our customers and helping you guys deploy successful power solutions. So I hope you all enjoy. I'll be in the Zoom, and if I can watch the chat if anybody needs anything. Otherwise, it's their rodeo. So good luck, boys.
I love the automation that we have set up that Ryan keeps on forgetting we have. You're supposed to talk about your old brands and then introducing the new.
Everybody knows the old ones. It's all about you guys now. Go. Everybody knows. No, this is good. This is about you guys and power. So please.
Very good. Very good. Well, I don't want to speak for you, but I'm very excited to be part of the Apex team. It's it's a lot of great name brands, and hopefully we're bringing some value to the party.
And Ryan, you said this is going to be one powerful Zoom meeting, but there's one powerful demo that everyone going to Vegas is going to have to try to catch. We've got the reference level DSP 8000 XEs on display the 5th through the 8th. So that's during show hours for CES. The address is in the invite. If you need more information, please get with us. But we will have them available for audition between 3 and 5 p.m. each day. Essentially, Meridian headquarters is going to be there talking to various car suppliers, car manufacturers, and they wanted the XEs on display. And we said, well, we'll take advantage of the fact that we're going to do that. And we'll take advantage of the fact that we have the space, since you're going to be getting it, Meridian headquarters. This is for dealers that are interested. Come by and get a personal audition, and for end users. And I got to say, Ryan's done a great job at closing up end users in particular that have given this a listen. I think we've had these on display in 3 different locations in the past 4 months, and we've sold, shipped or ordered 3 different systems. So keep that in mind. If you happen to be or can be in the Vegas area during CES, make an appointment with Ryan to come check the XEs out. All right, that's it for housekeeping. We're going to go into our power discussion today, and this was meant to be a 101 course. So if you're in for English or math, you're going to go down the hall. You're in the wrong classroom. This is our basics, and we wanted to set the level playing field so we could start tomorrow with a more advanced session. So again, these are going to be recorded. If you want to jet and go do something that you've got to get done, feel free to do so. If you want to sort of pay attention, interact here and there, please do so. But at your leisure, you can rewatch. We're going to post this probably within minutes of it ending. Vince Luciani is going to kick us off. If you don't know Vince, he was our senior sales engineer over at Surgex when he and I both worked together at Amatec. I came over with Ryan in June, and shortly thereafter, we were able to create a position for Vince, and it's just been a home run ever since, because I like to say I bring the beauty and he brings the brains. But you can tell he's an attractive dude, and he's got the brains. Yeah. So with that, Vince, why don't you get us going?
Well, you know what? You never know what's going to come out of Jimmy's mouth, and we no different today. Anyway, what we're going to talk about today: power generation, transmission, and distribution. I think it's kind of important to kind of go back to the square one, right? And talk about how how power gets to us. And then, once you're in the residence, just, how power is distributed within the residence, because those are kind of 2 different, 2 different challenges, right? And then we're going to talk about power disturbances, because those power disturbances, a lot of them come from either on the power generation and distribution side, or sometimes in the house. And then we're going to talk about how power disturbances affect today's electronics. And that's really why we have curated this line of power protection and power improvement products, right? That we'll be talking more. Tomorrow is going to be more about the product side. We just want to do the background today. So why are we covering this? And it's really to show you that power delivery is not a slam dunk. It is, it's kind of, it's very monumental. And actually, if you're reading in the news, we're getting a lot of stories about how fragile our power distribution system is. So it's definitely on a lot of people's minds, right? So let's just start from the beginning, the generation station, right? It's funny, power is generated just microseconds before it's used. So the turbines are turning the generators as we speak. We have one here in the Charlotte area, and you've got your own power distribution plants near you, but they're generating it real time. So what's going on at the plant? If you know anything about a generator, it's basically a motor that is running in reverse. In other words, instead of putting power into a motor, electrical power into a motor to cause a rotation to occur, a generator is you rotate, a magnet with windings wrapped around it, and that causes an electrical current in the wire. So the way that they build these generators is they have 3 sets of windings that are spaced equally apart. Then, as far as it is rotationally, they're 120 degrees apart. And why that is important is because it creates 3 sine waves simultaneously, right? So they could have very easily put 4 windings on there and put them at 90 degrees apart, and we would have called that 4-phase power instead of 3-phase power. But this is where 3-phase power comes from, is the fact that those generators have 3 windings that are creating these sine waves. But you can see the sine waves don't all line up. They're not right on top of each other. But we'll talk a little bit more about 3-phase as we go along. Just interestingly enough, right? Like I said, usually what happens is, some kind of fossil fuel, something is burned that boils water. The water turns into steam. The steam pushes these turbines. The central shaft on the turbine is connected to those generators, and that is what's doing the spinning. Natural gas is still a big part of our U.S. base, but we had huge news today. I don't know if you heard, but I think it's was it Lawrence Livermore Lab out in California successfully did cold fusion, which is another heat source that if that one is up and running, in the next 20 years, this makeup, if that turn out to be good experiments, this makeup will probably change a bit. So getting back to the main the main map here, that center section that you see there in blue, that is the transmission side. So on the generator side, I didn't even talk very much about what is the voltage at the generator. That's really not important, because right out of the generating station, they go directly into a step-up transformer that cranks the voltage way up to, as you can see here, anywhere from 138 to over 700,000 volts. The reason why they crank it up so high is because power is voltage times current. So for a given amount of power that the generating plant generates, if the voltage goes way up, the current goes way down. And when you put current through a wire, you minimize losses, right? So it's just kind of like if you think about, if you want to transfer the most power from your power amp to your loudspeaker, you're going to use really thick wire, right? Because you want to minimize those losses. Well, similarly, right? If you crank the voltage way up and you got really low current, you go through those transmission lines, you minimize that loss. The next step is to go to substations that are in our neighborhoods and different parts through the city. That's when it gets stepped down. It gets stepped down to different levels. It's kind of funny that in the world of power, the hundreds of thousands of voltage is called high voltage. They call medium voltage this 26,000 and 13,000 and 4,000 volts. Low voltage is what we use. We use 120 and 240 volts, at our location. I think that's kind of funny. Just little interesting tidbits. You got 3 power grids, right? So it's all of the power these, in these 3 areas, all of these stations are hooked together on the same grid, which allows power companies to share resources. So if there's one particular power plant that's at full capacity, or maybe they're having a problem, if another power plant has capacity, they can hook onto the network, or they're already hooked onto the network, but they have relays that they can switch and share power. So you got the eastern grid, you got the western grid, and then you've got the folks in Texas that needed to have their own grid, so they made their own grid, which kind of got them into a little bit of trouble. Last year or 2 years ago, when they the cold weather came and froze all of the natural gas lines and prevented them from creating electricity. Let's talk about now that we're past the generation and the transmission. Now let's go into the distribution. Why is it that we have 240 volts as the high voltage in our house? We have either 120 or 240. The way that it is derived, right? You might have 1, 2, or all 3 phases going into your neighborhood, right? I can look outside. I live in a neighborhood that was built in the 50s, and we have all overground, terrestrial power lines, they call it. I don't have 3 lines that are high voltage. I only have 1. And I think I asked my guy, he said it was 1300 volts is that particular line. In this example, I showed that you're tapping off a 2, it goes to a transformer. Here's for those that know schematics, this is what the transformer looks like. In this example, there's a 720 volts going to the input of the transformer. On the output, it has windings so that you have.
Can you hear me?
Yes. Yep. Anybody got a question? Anyway, we'll keep on going. You can get a 220 volt phases, and if you go across those 2 phases, that's where the 240 volts come from. So if you're looking at it from an oscilloscope, the output of that transformer is putting out 2 sine waves that are equal yet opposite in their phase. Okay, so the blue one is phase A, the kind of the yellow one is phase B. If you just use one of those phases, in the neutral line, so one hot and one neutral, you get 120 volt. Either phase, it doesn't matter. But if you go across the 2 phases, that's where you get 240 volts. So why do we need 240 volt, in a house? Well, your electric oven needs to pull a lot of power. So one way you could do it, you could run your oven off 120 volts, but you'd really need thick wire to be able to supply the current, because remember, power is voltage times current. So if the voltage is low, the current's got to go high in order to come up with that same number. But they found it's much easier, much more cost effective, that if we just power our high power devices like ovens and electric dryers and HVAC systems, that kind of thing, off of 240 volts, the wire size can be much smaller and it's much more economical. We've got a lot of discussions, right, when we're talking with our dealers, our partners, right? And I think Jimmy and I kind of have that viewpoint that we're partners, right? We're your in-house consultants for power. Sometimes we come across 3-phase service going to a house, and it's not a real clear answer, why you get 3 phases in a house versus 2 phases, but it all boils down to how big the house is, how much powered load is that house is going to have, and really what service is available. Like if I wanted 3-phase at this house, I couldn't get it because I've only got 1 phase up there on the line. But if you have a rather large estate and the power company just happens to have all 3 phases available to you, the contract engineer or the electrical contractor may choose to power it off of 3 phases. And we shouldn't really get bent out of shape. It's really not all that daunting. All it means is that you're pulling from all 3 phases that are coming from the power company on those transmission lines. You're going through a transformer and you're knocking it down to 320 volt phases, right? That's all. So it's almost like I was telling somebody, we were talking today, we're always talking about power, Jimmy and I, and it's like, you can think of it as, if you want to give it an analogy to a water system. Let's say you had a big house and you need a lot of water. right? Well, you could put a 1-inch line, but that's not enough capacity. But you might be able to put a big 2-inch line, but the water company may not have enough availability of pressure wise to push 2 inches of water down there. So they'll just give you 1, 2, or 3 1-inch lines. That's a bit same thing, right? That's what these 3 phases are. It's just 3 different 120 volt circuits. The reason why it's 208 is, well, first of all, if you're using just one of those phases, it's that same 120 volts that you're getting on that split phase 240 volts example. But if you go between any of the 2 phases, instead of going from a peak on one phase to a valley on the other phase, you got a peak on one phase, you're not quite going to the valley. So the value is 208 volts rather than 240 volts, really. And that's really the only difference between 240 volt split phase and 208 volt service. It just kind of depends on what the raw service is out there that's available to you. So let's getting back to a 240 single phase. Now, one thing I get a lot of questions: what is single phase? What is split phase? What does that mean? So for some reason, our brethren in the electrical world, right, the electricians of the world, even though the 240 volt is 2 phases, they still refer to that as single phase, which to me, I understand that, right? I'm in the biz, but I'm trying to help you guys understand it. So you'll hear me refer to it as split phase, just to remind you, while we're talking, that we're talking really about 2 hot phases that are going on. So both of those things mean the same thing, single phase or split phase. The 2 phases and a neutral line that are coming out of that transformer. Now, transformers, one thing I didn't mention before, a transformer, you may have 1 transformer for one house. In my neighborhood, I have 1 transformer I can see out there, and it is powering 3 houses around here. But I think you said in your neighborhood, you have about 5 or 6.
Yeah, 5 or 6.
Yeah.
4, 5, 6, 8. I've heard all those numbers. Yeah, depending on
120,
the size of the neighborhood,
121, whatever
it
it takes.
Yeah.
So anyway, what that means is that any kind of power disturbance that, let's say my neighbor had a wood shop that is like right near the backyard, because these power lines usually are on the telephone poles on the demarcation between property line. If his wood shop was right there and he cranked up his table saw, he could backfeed noise that gets back onto the line. Since we're sitting on the same side of the transformer, that noise could infiltrate into my service. So that's one of the reasons why we're big proponents of the solutions that we have. And again, we'll talk about those solutions tomorrow. But so what is the purpose of this breaker panel? So circuit breakers are there to protect the wire. If you put too much current through a wire, you're gonna get, the wire will get hot, and the longer that current flows through it, the heat builds up and the wire could catch on fire. So that's why you have circuit breakers. The main breaker you can see there is really to protect the supply wires coming in. The individual circuit breakers are there to protect the wires that are going out to the branch circuits. So one thing that is really interesting is if you total up the breaker values of these individual breakers, they often exceed by quite a bit, 2 or 3 times is higher than the main breaker. And you say, well, how can that be? It's like I have the possibility of pulling 400 or 600 amps, yet my service is only 200 amps. Well, the reason why that is because we know that you're not going to have everything on all the time, right, in the house. There's going to be some things on, and this is kind of a gut call from the electrician. They have a lot of experience and they kind of know what to put on what phase, and they're going to do some phase balancing. You really want to pull from the 2 phases as evenly as you can. It doesn't have to be exactly perfect, but you want to do that. So that's kind of how it works. So when you look at your breaker panel, if it adds up more than the main breaker, that's not the end of the world. So in the breaker panel, if you go down the left side or the right side, I just have the left side marked here. The two phases alternate. So the first breaker is phase A, then phase B, then A, B, A, B, A, B. The reason why they do that, if you can see on your screen that top breaker that is 125 amps, there's a little, it's usually a little metal clip that goes over the little, the actuators, right? The little handles on there. That means that those two are physically linked together. And if one of those breakers should trip, it's going to automatically trip the other breaker, because if you have, a 240 volt oven that has two hot lines going to it, if one of them is to trip, the other one you want to go ahead and disconnect as well. So that's the telltale sign, if they're connected together, that it's probably a 240 volt load. So just continuing on, let's look a little, dig down a little bit deeper. This is, the sine wave that you see on the right hand side. That is a perfect sine wave. And if all of our power looked that clean coming out of the wall, then Jimmy and I would be selling something else. I don't know, you'd be selling bourbon probably. No,
The water used to make bourbon.
oh yeah, okay, yeah. Special purpose water.
That's right.
So 60 hertz, right? You've heard of 60 hertz, 120 volts. 60 hertz refers to how often it does its transition from a 0 up to a peak of 170, down to a valley of minus 170, and then back to 0, right? You could take it from one peak to another peak. It's the same thing. That's what 60 hertz means. It means it happens 60 times a second. We refer to this as 120 volts RMS. For some reason in the world of electrical engineering, they decided to refer to power signals based on their average value, so that the 120 volts V is really an RMS, a root mean squared. It's just it's a way of finding the average, right? But it's really peaking up to 170 whether you kind of picked up on it or not. There are certain times when the voltage is actually 0, then it goes up to 170, back to 0, and down to 170. But it's happening so quick, you don't want to start touching it and seeing when you can touch when it's at 0. But technically it's 0 at some time. Over here, the plugs examples that I have on the left side of the page, the ones that we see most commonly for 120 volt service, we have the NEMA 5-15R and the 520R. So the 515R, as you can see, is the one you see all the time, right? The two vertical blades. The larger of the two blades is the neutral line. If your house, if the wiring is connected correctly, right, and there's no issues with either any loads or any wires crossed in the system, the neutral wire should be 0 volts, and that should be safe to touch, as the ground wire is 0 volts. The hot wire is this line, and it's the shorter one. In the world of NEMA, 5 means it's a 125 volt max. That means we use it for our 120 volt service, but it's 125 volt max system. 15 is the current level, 15 amps. R means it's a receptacle. On the other side, you can see a 20 amp, a true 520 outlet. The hot would be vertical, as you see here, and the neutral line is actually horizontal if you have a 20 amp load. And I think we have, like, this UPS is a 20 amp UPS, and you can see and this presents a lot of frustration for our dealers when they order a 20 amp product. It's going to come with the plug horizontal. I don't know if everybody can see that there. I mean, here it's a little closer, closer look. You see how that is? So that would only plug into a 20 amp outlet. So what that does is it prevents that 20 amp load from plugging into a 15 amp outlet, right? Because if you did that, you would blow the breaker, and it would be a pain in the butt.
Couldn't we just chop it off and make our own?
You could, but that would be wrong, because what would happen is you would be putting a 20 amp load on a 15 amp circuit.
That's not good.
Unless you want to rig up a way to turn the breaker on all the time.
But we can go the other way, can't we?
Yeah, we can. That's why they make these outlets accept a 20 amp outlet will accept both a 20 amp load or a 15 amp load. And that's what we call that a T outlet. So anyway, if you're if you're able to spec, and we've got, I think, best practices in here, what to do, ask for those T outlets so you plug 15s and 20s in there. So unless you specify otherwise, this is how an electrician is going to hook up your outlets in your in your equipment closet, right? They are going to most likely use a 15 amp circuit. The black wire is the energized wire, the hot wire. It gets hooked to the circuit breaker, which is connected, of course, to this black phase B here, right? The white wire is the neutral wire. It's going to be connected to a bus bar, right? And this bus bar is also connected to the neutral, coming from the transformer, but it also is going into ground rods that is for a lightning protection. It's really just a path that if the system should get hit by lightning, there needs to be a path for that lightning to go, and that's really where that's go. What's interesting to note is that neutral and ground get terminated to that same bar, right? So what that means is that the intention is that neutral and ground are connected together. And if you have a voltmeter and you test the voltage between 2 points that are connected together, you get 0 volts, right? They're shorted together. So the intention is neutral and ground should be 0 volts. And we'll get to that later, probably tomorrow, when we talk about isolation transformers and why they're good. But remember, neutral and ground are intended to be connected together. The other thing to point out, these outlets over here, they're usually cascaded, right? If there was a individual breaker for every outlet and every lighting circuit in your house, your breaker panel would probably be 3 or 4 columns long, and it would be just very much a waste. Because if you think about it, if you had 4 outlets in a hallway, what is the likelihood you're going to use all 4 of them at the same time? Very low. So we'll just put them all on the same circuit. That is okay for a hallway, not okay for a theater closet, right? We want individual outlets. We only want 1 outlet on 1 breaker, and instead of it being a 15 amp outlet, we want it to be a 20 amp outlet, so you get bigger wire, right? Bigger wire, what does that mean? More current handling capability, less losses when there's a large current draw.
So stop on that point really quick, because that actually, what I hear from, usually it's like the audiophile type, it could be the homeowner. Hey, we have a dedicated 20. How do you have good power? Oh, I have good power. I have a dedicated 20 amp circuit.
Yeah.
That really goes to the point you just made about lowering impedance. It does not mean necessarily that it's clean.
Oh, correct. Because there could be things polluting it upstream. It's definitely on our list of best practices, to have dedicated outlets. It helps with it, but it's not a guarantee that that outlet is not a problem.
And the other thing these dealers fight quite often, they ask for the 20 amp circuit, which they got, but at the wall outlet is that NEMA 515R.
Yeah.
And I mean, that's pennies. You just get it swapped out.
Yeah.
Put a 20.
Yeah.
A 520R.
But you have to ensure that the wire is the right gauge. So in general, the National Electric Code says if you have a 20 amp circuit, you're supposed to use a 12 gauge wire. If it's a 15 amp circuit, you can go to a 14 gauge wire. I like saying, just being very proactive and say, in my equipment closet, I want a dedicated 20 amp circuits, but I'd like for you to use 10 gauge wire. So it's back to that using bigger, thicker speaker wire. We know, the more copper you have there, the lower the impedances are going to be, the lower the losses are going to be. So,
Makes sense.
crank it up to 10 gauge if you can. So just for completeness, I just showed how a higher voltage, a 240 volt outlet is connected. I used the locking style. I think when you have a big hefty connector, we're in an industry that everybody does everything first class. You want to use a locking connector. I just happen to use the locking connector that is 4-wire. So what's the difference between a 4-wire and a 3-wire? The 4-wire has the 2 hots. So if in the piece of load equipment, they need 240 voltage, they will just, go between L1 and L2 and use those 2 wires. But sometimes, it costs money to take 240 volts and bring it down to 5 volts DC, right? Well, it's a whole lot cheaper if I can take 120 volts and turn it into 5 volts DC. Right. So if on my piece of equipment, I include the need for a neutral wire, then inside that piece of equipment, I can go between either one of these phases and neutral and get 120 volts. So you'll see both 3-wire and 4-wire. I think that, if you have like a really low end dryer that all it is a turn knob and you're just, they only use 240 volts. There's no reason to have that other wire. But if you have an electronic dryer that has an LCD panel on it, most likely it'll be a 4-wire. So anyway, just not completely important, but just for completeness. All right, getting back to what power would look like if it was absolutely perfect, right? This is the goal. This is what we're looking for. But a lot of times we know we don't get that, right?
No.
Jimmy, you've been working in this biz a long time, and you've run across this. The ones that get all the press, voltage surges, surges are these instantaneous changes in voltage level, right? And they could go, they could go to the positive side, they go to the negative side, they could be, individual single events, they could have, be events that have a lot of ringing going on. What I have shown here is just an example. The amplitude between this 170 volts, by interpolation, maybe that's 340 volts. This thing could be as high as 60 or 6,000 volts, not 60,000. Well, I guess it could be 60,000 volts.
Sure.
Mother Nature packs a punch, but it could go very, very, very higher.
Well, what we could say is 6,000 volts at 3,000 amps would be enough to shred the Romex in the wall. And I have heard cases where I had one in New Jersey once where a homeowner said that the utility agreed, confirmed that they had 10,000 volts come into a neighborhood. So yeah, he definitely had Romex shredding.
Yeah. And this is part of the reason the 2001 National Electric Code got updated.
2021.
Yeah, do what I say.
2001.
Oh yeah, no, that would have been a long time ago.
That was updated.
That was before electricity was invented. Yes, 2021 required that on new builds going forward, you got to put a whole house surge arrestor on. And big fan of surge arresters. Even in our time at our previous company, we suggested surge arresters at the service entrance, even though we didn't sell any of them.
Yeah.
And that's to just kind of get it down as much as you can. Still big believer of needing surge protection all along, because you don't know where it's getting in. Sometimes it comes through the service entrance. Sometimes it gets on a speaker wire and then goes through your power amplifier and then gets back on the power line and goes through the back door. So proper surge protection is very comprehensive. The drawing on the right, this is showing over voltage. Now, a lot of people get confused. A surge is an over voltage. What's the difference?
Yeah.
We refer to a surge as those instantaneous spikes. They're also called transient spikes. Thank you. Yes, brain dead over here. But Howard, the picture on the right, that kind of over voltage is when the sine wave itself increases in amplitude. Usually when you have a sine wave changing its amplitude, it has to do with the transmission and distribution part of the delivery chain, right? The power company does a great job when they're generating whatever voltage their target is. They got pretty much control on there. But once it starts going through these transformers, if the transformer connections get loose, sometimes it can cause a change in these voltage levels. A lot of times it goes over voltage, and sometimes it goes, you have an over voltage condition, And the remedy is an electrician needs to come out and tighten up a wire, which means it's sustained for a very, very long period of time, right? So that's that's definitely an issue. The power could also go under its level. A couple of reasons for that. Sometimes you have voltage sags, which are very short-lived voltage fluctuations, usually in the downward, in that direction. If the voltage is reduced and it stays that way for a long time, that's called a brownout situation. Where do brownouts come from? Overuse of the grid, right? Too many people using stuff, and a lot of times these brownout situations occur during the summertime. There's just not enough capacity for generation. Businesses still have their ACs cranked on because it's the summertime. People go home at 5 o'clock, turn their ACs on, and it just, it's just not enough juice to power anything, and then sometimes we see situations because, Jimmy and I did a lot of analysis, right? Using an electrical analysis tool. Sometimes it's a fluctuation both on the low side and on the high side. Again,
wiring issues either in the home or outside. I was just in Florida for the CEDIA Tech Summits. Victor said hey to me. He's a dealer in Naples, Victor.
Yeah.
And he had mentioned that he had some wacky issues going on. You just reviewed a diagnostic log, I believe, and it was nuts, right? You said it was like one of the worst you'd seen.
He showed us data that was in service for 108 days, and the number of outages and voltage fluctuation, I was like, what the heck is going on?
So you've certainly uncovered wiring issues inside the home. We've also been able to rule those out and point to the transformer outside of the home.
Yeah.
And I think you'd agree with me that coastal properties, probably more so than almost anywhere, especially if we're dealing with high salt in the air. Transformers corroding seems to be like a more prominent issue.
Absolutely. I had an issue here. The transformer is literally on the other side of my driveway that powers us in 2 other homes or 3 other homes. And I was watching television. The television was on, everything was good, but the lights behind me were flashing. And I knew, okay, I've got one phase is wrong. The power company came out, and sure enough, the crimp connection between one leg of the transformer and the distribution wires was loose. It was intermittent. So only one of the phases was flashing, the other phase was okay.
And that's the kind of thing that hits a dealer where they have intermittent issues. Hey, come out, this thing's not working. They're out, it's working.
Yeah.
They leave, hey, it's not working again.
Yeah.
And of course, the dealer's getting blamed because it's their thing that doesn't work. That's the challenge of it all.
And my issue showed itself on a misty, rainy night, right, where there's some corrosion just got in between that crimp connection, and and it was an issue. So the last power disturbance that we're going to talk about, high frequency electrical noise. Where does this come from? It could come from the Wi-Fi and all of the wireless devices. You think about Romex that is traveling 75 feet through the walls of your house. They're basically big antennas that are picking up all kinds of noise. But a lot of times this kind of ugly looking disturbance of electrical noise can come from a power tool or something like that, or an air conditioner turning on and turning off. Although that's more of a transient device, we didn't talk about it. It causes that. But so it's so again, these are all issues. So I get the question all the time, big deal. So you got these issues.
Does everybody have these issues?
I think we've seen that. I think there was we probably looked at over 1,000 logs in the time that we were there. And I think there were 2 occasions where the data set showed perfect power for 3 months. And it's like, well, that doesn't sound right. So we called the dealer. It's like, where did you plug this data analyzer into? And we plugged it in the back of one of your UPSs. Isn't that where I was supposed to plug it in? It's like, If you want to show how perfect the UPS works, then yes, that would be a good place to do it. But if you wanted to show how lousy the power company is, no, you need to put it on the other side. But how does this manifest itself, in our electronics? Well, I put this graphic together, and I'm getting a little bit more in the weeds, but I'm talking to a bunch of technical people, so I think you'll be with me here. So this picture here is a digital pulse train, right? I'm sending that data down the line. A digital bit stream is either going to be ones or zeros, right? The zeros are usually ground level, right? 0 volts, and the ones can be, if it's TTL, it could be 5 volts. If it's, some newer technology, it could be 3.3 volts. If it's some of the video formats, it could be 1.8 or even 1.3 volts. I make that point because the difference between what a 1 or what a 0 and a 1 is, the faster the technology comes, the smaller the difference between these two are. So when you have a digital communication, the way that you set it up is you have to have an agreement between the sending chip and the receiving chip, right? To say, okay, what are we going to say a high is? What are we going to say a low is? So they set those thresholds, not at the top and not quite at the bottom. And they say, okay, anything before, above V and high, we're calling that a 1. Anything below V and low, we're going to call that a 0. And you can see I've superimposed that over an actual oscilloscope reading of a digital bit stream. So what happens is these power disturbances are actually corrupting the communication line. The digital. We think of digital. I think we traded one issue in for another. If you think of this as if this was an analog video signal, right, and it corrupted it that much, you're going to get snowy picture. It's going to look lousy. You may even lose sync and all that kind of. Oh, but now we got digital, right? So what does that mean? Well, if I send that digital bit stream, right, what's going to happen? My intention on that third bit was for it to be a 0, but noise pushed it up above V and high. So I might interpret that as a 1, right? And down low, I was supposed to, down further down, I was supposed to transmit 2 zeros in a row. Well, one of the zeros got there, the other 0 kind of got noised up into the 1. This is called bit errors, right? And this is why they had to invent bit error software, right? Mm-hmm. To kind of say, what do I expect it to be, that kind of thing. Anytime that your bit error correction is kicked in, it's not going to get it right 100%. It improves, but a better improvement would be to clean up your power so your digital bit stream doesn't look that lousy. So noise and power disturbances are not the only thing that is screwing up our power. We just got off a call with another manufacturer. And that manufacturer was saying, good Lord, the number of switch mode power supplies that we have in our systems, it's backfeeding, noise back onto our line. Because remember, even if we're using dedicated lines, right? I got a dedicated circuit, 20 amp circuit for rack 1 and another dedicated for rack 2. Well, everything in rack 1 is on the same power bus, right? Mm-hmm. So what I have here is
by the way, it's all going back to the possibly same panel,
same sub panel, and could be disturbing other. Yeah, absolutely correct. Absolutely correct. So one thing that when you start looking into the weeds of how power is consumed by a piece of electronics, that red, of course, is our voltage sine wave, right? That light blue color is the current draw of a non-power factor corrected power supply, all right? And usually this is a switch mode power supply, right? So what this means, the way that you interpret this is I'm not pulling current from the supply commensurate or even with that sine wave. I'm pulling current only when the sine wave's at its peak. What that allows me to do is pull maximum power instantaneously. And then it's like, all right, there's not enough juice down in this section. So I'm just going to wait and I'm going to pull it again when I get to the peak. Well, how that manifests itself is by corrupting the voltage waveform. As you can see, here's an actual unit. Here's the current draw in blue. And as you can see, as the current draw gets to its peak, I am corrupting or flat topping the sine wave. Well, if I'm on the same bus, power bus, right, I'm getting crummy voltage levels to my, ancillary or neighbor piece of equipment. So it's not always these external things in the world that is causing power power issues. It's also the stuff that we plug in. So what that leads us to is some of our power supplies are power factor corrected, so it pulls current in sync with the voltage waveform, and that helps a little bit, but not always. So the bottom line, let's cut to the chase. The semiconductor industry, at the urging of the Consumer Electronics Industry Association, the Consumer Electronics Association, it is, member of companies, they all get together. It's like, all right, we're going to share best practices. I know some of us are competitors, but let's all, figure out what is the best ways to let equipment last long. So the Electronics Industry Association has some guidelines. Consumer electronics products, they should be lasting anywhere from 5 to 7 years. You can't make a piece of equipment, every piece of equipment, last 20 years. You could do it, but you might price your piece of equipment way out of price, right? So if you think about it, right, those CD players, do I still have one? I think I used to have a whole stack of CD players over there. I think I've thrown them all away because they all died. Why? They lasted their entire life, or maybe they didn't last their entire life. So the three categories that the semiconductor industry, when they did their studies trying to answer to the Electronic Industry Association, they said, send me your equipment. Let's do some testing on our ICs. They broke their findings down into three categories. Immediate end of life, meaning one electrical event mapped out to immediate failure. The one that to me was the most eye-opening was this new category called premature end of life. And what they do is they took and they did a what is referred to as a Monte Carlo analysis. They take every single piece of component that's in, for instance, that cheap $79 CD player, and they'll say, okay, what is the odds of this particular device, given tolerances and whatnot, failing prematurely, or or what is the number of years that it should last? And they put all of that stuff into a spreadsheet and come up with this particular device should last X number of years. Well, if it doesn't last the X number of years that it's supposed to last, that is called premature failure. The last one is another eye opener. They found that that sometimes equipment locks up, right? And there's no damage to the equipment. It just, and I'm preaching to the choir here, requires a reboot.
You think these guys reboot?
I'm sure they've run across that. Actually, it's funny how in our industry, the power industry responded for your guys to need to reboot by giving you IP-enabled devices that allow you to reboot remotely. We didn't say, hey, let's solve the problem of rebooting. We just gave you a Band-Aid to say, if it needs rebooting, at least you don't have to roll a truck. That's not our philosophy. What we're trying to do is get rid of the need to reboot. So what, when you look at this, look at how many of these issues map over to, lockup issues.
Mhm.
A lot of power disturbances, a map over to lockup, and of course, premature life. But the funny thing about it, the early days of power protection, heat on, immediate end of life. That was really what, what the products that were out there.
It wasn't really until power quality became, something that we looked for after and tried to, condition for.
Yeah.
Right. That's when we started like, power quality means a lot more than just surge.
Yeah, I think so. So we talked about, we were gonna share with you what our best practices are. I continue to be impressed by the amount of detail and the amount of engineering that goes into the systems that these guys put together. I'm thoroughly impressed with the fact that a typical AV dealer knows a great deal about the ever-changing video front. I mean, there's a lot going on there. They're up on audio. They're up on distributing audio and video. Oh, and by the way, let's get into the lighting biz. Okay,
And
well,
the
let's
shades.
gotta get
And the
shades.
animation.
Because we gotta tie all that together. Oh, security. You need cameras?
Yeah, sure.
Cameras. You gotta know a lot about everything. So, the one thing that you do a great job is you do a power audit, right? You know how much power you need. Request more than you need, right? Ask for more. If they give you less, at least you get what you want, right? You probably already know this, to keep those high current loads on separate circuits, right? Keep the lower current loads on one. We don't want the high current loads disturbing, what's going on those low current sides. Dedicated outlets, we talked about those. The definition of a dedicated outlet: a home run of all three conductors. I've seen a couple of situations where the dealer said, yes, I asked for dedicated outlets. What does that mean exactly? Okay, well, the hot wire was run and dedicated to one outlet, and then the neutral wire, you opened up the outlet and there's two wires on there. It's like, why is there two wires on the neutral? That neutral's going somewhere else.
Yeah.
It's like, that's not dedicated.
Maybe the lighting can.
Yeah, man.
The ceiling fan.
Yeah, who knows?
Yeah.
They need to pick up a neutral somewhere. All three conductors, line, neutral, and ground, home run from the outlet back to the breaker panel. We said this before, just go ahead and ask for 20 amps.
So we did have a question earlier about this. Someone was getting disconnected, phone was jarbled, and they said, hey, did you say you could use a 20 amp receptacle on a 15 amp circuit? And actually it was quite the opposite. It's good to use a 15 amp receptacle wall outlet on a 20 amp circuit all day long. Don't flop those around.
Yeah.
You never want to be in a position where you're susceptible to draw more than what's available at the circuit.
Yeah, the whole NEMA system was set up to make it as easy to make sure you don't make a mistake, right? So they made it physically so you cannot plug a 20 amp load into a 15 amp circuit, right? What will happen if you did that? Let's say you cut your connector off on your 20 amp load, or you used an adapter to plug it in. All you're doing is, screwing yourself, because what's going to happen is, it may not be on day one, but sometime that 20 amp load is going to pull the full 20 amps. It's going to trip that breaker. You're going to get the service call, and all you're going to do is you're going to bring it over and reset that breaker until the next time you trip that breaker. So you never want to do that. And the thing is, you never want to also change the outlet. The outlet has to match, whether it is a 520 or a 515, has to match the wire and the breaker that's on the other side. So
don't just change the wall outlet, like I had said earlier.
Yeah.
Don't just change the wall outlet without confirming first that the Romex is the right size for that breaker.
And the breaker value is the right value. Yeah. Because remember, you can use a larger wire that's legal, right? You know, they actually they suggest doing that if you have a longer wire runs that is, you know, longer than 125 feet, you're supposed to increase the gauge by 1. It's just the rule of thumb.
So you had mentioned runs for all 3 conductors. Does that meet the requirements or definition of an isolated ground? So actually,
Very good.
I mean, actually, though, there are structures that have their own isolated ground.
So,
right,
so,
throughout.
so the definition of isolated ground in the world of electrical is that, all right, so a dedicated outlet is what we've already described. One outlet goes to one breaker and all 3 conductors are there. An isolated outlet really refers to commercial establishments where the conduit is metallic. Okay. And when you have metallic conduit, you know, a lot of times when you have, you know, when you're using conduit, instead of Romex, where all 3 wires are in one jacket, you're using individual conductors. You use, you know, you got a, you know, it's a black wire, and then you pull a white wire, and then you pull a copper wire that is bare, right? Because that's a little less expensive than putting the green jacket around that on that wire. Well, if you put that through the electrical conduit, the bare wire is going to come in contact with the electrical conduit. Now you have 2 paths for the ground. Okay. When you have an isolated circuit, National Electric Code dictates that the ground wire be insulated with the green jacket, so it doesn't come in contact with the conduit. And then you got to use a special outlet. Most outlets, when you affix it to a metal junction box, it's really not a junction box, but, you know, an outlet box, right? The conduit is terminated to that, and it's got a, you know, a metal nut. The box is also conductive, and when you put the outlet on there, if you don't use a special isolated outlet, that outlet will actually connect the ground to the metal box. So now you have, again, 2 paths. You got the wire and you've got the box. Isolated means special outlet where the tabs are isolated from the ground. And then when you use the green wire that is insulated, it means that ground is only that green wire, and the conduit is taken out of the picture. It is not connected. And there are certain in the world of isolated, certain cases where you want that. It's usually in hospital or industrial. You know, I don't remember the exact use case where that becomes an issue, but that's the reason why you're doing it.
Okay.
All right. I'm a big fan of running larger wire, right? Especially if your wire run, and remember, when you're calculating your wire run, it is from the outlet up, over, down, whatever path it's taken. Just don't measure and say, oh yeah, it's about 30 feet. The complete wire distance, you know. And, you know, I wrote in here 125, absolutely. But if you're at 90, if you're at 100, go ahead and ask for the larger wire, right? There's no code restriction to using a larger wire. You just can't use a smaller wire. Okay.
Kind of similar to that question we had earlier about outlet size and circuit.
Yeah. Yeah. So this is just kind of good practice. And, you know, and this is more important if you're, you know, if you don't choose to use one of the you know, the power correction products that we're going to be talking about tomorrow. If you don't have any of that stuff, it's good practice to get connected equipment on the same phase. But so you remember in our breaker panel example, it's A, you know, phase A, phase B, phase A, phase B, phase A. So it's like, just ask your electrician, hey, everything that's going on my stuff, put it on phase A, right? And sometimes it's not a guarantee that if you mix your phases that you're going to have a problem. It's just that if you just use the same phase all the time, you're reducing that. Now, when you get to our large format UPSs that have 2 phases coming out of it, it's not quite as critical to do that because, you know, we've
We've
isolated that, yeah, that
load,
whole
yeah.
thing. So it's not nearly as much of a problem then. So, you know, what is the best practice? I don't know, Jimmy, what is this last one? What is the best thing that you should do?
Well, you should use a voltage regulating online double conversion UPS.
Oh, really?
And I said it in the opposite order. But at any rate, the point is voltage regulation coming out of a double conversion online UPS is absolutely one of the biggest things that you could add to your business. If you don't already use one from a myriad of people that sell them, you should be using it because that will take care of so many of those power issues that were brought up.
So Jimmy, you predate me in the CEDIA channel and specifically the power channel. You've been here a long time.
Thanks. Yeah.
You know, you're an old dude.
No.
But no, but seriously,
Yeah.
You were at the forefront of introducing this technology into this market. And, you know, it's anecdotal evidence, but it's evidence nonetheless. When double conversion online UPSs, and especially large formats that have isolation transformers built in, what did you see and what kind of feedback did you get from your dealer network when you started really looking at power?
So, you know, often I would say that in really 2012 to 14, the channel was just reactionary. Somebody called, oh crap, we got to reboot something, right? We rebooted and it took care of the problem. Then, you know, years and years of rebooting goes by and it's like, why do we have to keep rebooting? The homeowners have to be asking, why do we continue to reboot this stuff? Why doesn't it just work? Well, power is the variable. And if you can control for that, then you can diminish, and I'm not saying eliminate, but you can diminish the need to react to interruption in the system performance.
Yeah.
Yeah, taking matters under your own control. And most of those large format UPSs that, you know, you and I had put together designs for and sent out to the field over the last few years, they were mostly retrofit.
Yeah.
And mostly they were dealers that came to us. These projects were, you know, problems through the roof. When those things went in, problems went away.
Yeah.
Yeah.
Yeah. You know, and, you know, the beauty of this technology, you know, and again, tomorrow we're going to do a deep dive into these products. You know, give us anything, right? I mean, you know, they accept a very wide voltage range, and it doesn't matter if the voltage is fluctuating around. We're going to do a demo tomorrow, a live demo where we're gonna take a variac, which is a transformer that you can vary the output voltage, and we give it to a UPS and then look at the output of the UPS on a oscilloscope, and it just, I don't care. I'm gonna put out 120 volts, perfect. So the bottom line, you know, why do I care? Why do I want to do this? You know, improves system performance. Where, you know, if you guys are on this call, that means you are, you know, dealers of Apex equipment, which is
the good stuff.
The good stuff.
Really good stuff.
You know, it's like, you know, so improving system performance is never a bad thing. We've already beat a dead horse about talking about reducing reboots and that kind of thing. But, you know, I think that one, you know, you got to think about it in a different way. I would say that most of the people on this call, their whole business model is predicated on referrals, right? And you know, I've run into this. I've been in power for, you know, 18 years, and I've never been in an industry selling power products where the device that is being sold, right, and you plug it into the wall, when it fails due to power issues, that the customer didn't say, your little box is awful. It needs rebooting all the time, right? They never say, hey, the power company is giving me bad power. You know, you get blamed, right? So it's really a reputation thing. And that's one of the beauties of this little secret, right? Is we're not asking the dealer to pay for it. We're asking you to sell it to your customer.
Yeah.
They're going to get great benefit out of it because their system will be available to them to use. It's going to perform better. It's going to extend the life of their system. But the benefit to you is you're not taking these calls, Super Bowl Sunday at 9 o'clock. Why did the damn system go down with 5 minutes left in the game? You piece of shit, pull the shit out.
You think they use language like that?
I don't know. I've never been a dealer. I'm just assuming.
They put up with a lot.
No. So that's all we have.
Tomorrow, we're going to talk about developing trends in power. So we get a lot of client rep, homeowners on occasion. They'll say, hey, I've got a generator. I'm good. I don't need your large format UPS. We get a lot of, I've got solar. Okay, that's wonderful. Wind, great. I'm looking at Sonnen. Okay, cool. I'm looking at Savant Power. I'm looking at Tesla, or something you have. And we're just there to say, hey, you probably want to look at both in one fashion or another. Maybe it's a smaller UPS that's a double conversion online voltage regulating unit that sits in the rack, or maybe it's something that drives a sub panel and you've got, more of a macro structure put in, infrastructure put in for an estate. This is down at the micro level, just driving the audio, video, and or lighting load. So tomorrow's presentation will be mostly about trying to clear up, any confusion, add some clarity if we can, when and where we can, about all the available, I would say platforms. It's both platforms and technologies that homeowners are getting faced with, that maybe you're getting faced with, and when and where should we use those? And that really, at the end of the day, Vince, the way we handle power is, what is the application and what is the end game? What is the result we're looking for? Do we want to stabilize power? Do we want to clean power? Do we want to do both of those? Then let's, ask some questions about what's the load look like? We had a nice LED wall presented to us about a week ago. And, if the goal were to make that shine, I might say, oh, we can stabilize power and make that shine. But the objective, number one objective, was just stability and power. They were in an area in Florida with some deep fluctuations. So we just want stable power going to the, what was it, 420 amp breakers worth of LED wall.
Yeah.
It was a nice one for sure. So what is the application and what is the end result we're trying to achieve? Tomorrow, we're going to talk a little bit more about that. For now, we are ahead of schedule a little bit. And what I'd like to do is open up for Q&A. The way I think it'd be best to do that is maybe just raise your hand. And then I can maybe unmute you so we don't have total chaos. Also, Randy Massey out of Georgia texted us a question. It's really more of a statement, I think, than a question. It's about the outlets. Yeah, we'll talk to Randy. We're gonna see him tomorrow. Sent you a pic. Oh, he said sent you a pic.
Yeah.
All right, cool. All right, well, thanks, Randy, for engaging us there. We'll see if there's any hands that go up, and then.
So another thing we're talking tomorrow, if you guys are interested, since we are in the category of power, and there is a lot of new kinds of technologies that are kind of under the umbrella of power, these whole house battery systems and that kind of stuff. We took the time to kind of look into it. And again, we're not, we're not here to bash any other manufacturer. I think, their solutions are valid for what they do. I just thought it'd be great to have one, place where we can say, what is the difference between all these things? What do they focus on? What do we focus on? Because I think that at the end of the day, I think it's a difference in philosophy, right? We are big proponents of power quality.
That's right.
And some of these other systems, that's not their main focus, which is fine. It's like
quantity of power.
Quantity and just availability of power and being off the grid and being green and that kind of stuff. But it's good to know the difference between what we do and what they do.
Sure. Yep. And just what's available to you. I mean, how often do we sell somebody something we don't sell?
Yeah.
It happens.
I-
You know, at the end
I
of the day, it's out there. The dealer's gonna find it one way or another. We might as well just help them get to that conclusion quicker.
Yeah.
Just say, hey, this is the stuff that's out there. What do you want?
Yeah.
What can you use? What do you need?
Oh,
Yeah. Well, I'm not seeing anybody chime in here, so I think that means that we probably covered everything. 100% clarity. Everyone received the message well. So appreciate the time that you all took to sit through this. It is being recorded. We will hit end here momentarily. We will save this and make sure it gets posted. If you want access to it, you'll probably need to just contact your local rep, and we'll make sure that we get that to you. If you happen to, if you want to reach out to Ryan or Vince or myself, please feel free to do so. We all share basically the same email address. It's just going to be Vince or Ryan or Jimmy ahead of
yeah.
@apex-tech.us. Okay, that's all, folks. Thank you.
Thanks, guys.
Thanks a bunch, guys.
Hit stop.
Where?
Thank you. That was really important. I'll see you all tomorrow.
Awesome.
Take care.
Bye.
Bye, everybody.